All right, let's get started. We have 30 slides, so we are short on time. So, welcome everyone to this year's talk about COCONUT-SVSM here at KVM Forum. We want to talk about progress, plans, and challenges. So, let's just jump in with the progress that we made in during the last year. So, yeah, a year is a long time. I did not get as far as I hoped to, but we nevertheless made some progress. So we made lots of enhancements towards more idiomatic Rust in the COCONUT-SVSM codebase, which made the code, I think, much more secure. The initial implementation was written mostly by C developers, and yeah, C developers not always know how to write idiomatic Rust, me included. So lots of improvements there. We got a lot of test improvements. So we now have a test runner that actually runs tests in the SVSM context, which is a big improvement because before that we could only run them in Linux user space, which kind of limits the ability of what we can test there. So we have now a test runner that runs in the SVSM context itself. And we also got fuzzers for certain subsystems like the ACPI table parser and the file system, for example, the file system implementation. A big change that we moved towards and which Roy worked on is that we moved to IGBM booting, which is a really great thing because it allows us to be more hypervisor independent. IGBM basically provides the full hypervisor interface that the SVSM needs. So it makes it more independent from that. What progress did we make on platform support? Yeah, the COCONUT-SVSM was written and is still mainly developed on SEV-SNP, which is great, which is a great platform. But of course, COCONUT wants to support other platforms as well. So work has started by Intel to make COCONUT-SVSM run on TDX partitioning. This is ongoing work. There are some challenges there, which I get into later, or which we get into later. TDX support is probably going to look a little bit different because the architecture is a bit different. So TDX does not have a strict need for an SVSM protocol, for example. They can handle everything by just handling the guest OS VE exceptions. And also something that started to appear is support for the native platform, so running in environments that do not have confidential computing hardware protection. Goal here is to make it run in the Hyper-V VSM mode, and KVM is also getting support for this at some point, so it will run there as well. So this is the progress on the platform support that we make. It's, of course, everything is still work in progress, but the work has started on these platforms as well. Another important progress that we made is that we got the TPM emulation code merged. So the SVSM now has a VTPM and is actually useful. So it now actually has a service to provide to the Linux OS. You can use it for runtime attestation. It is still an ephemeral TPM, so the EK is regenerated at every boot. So you cannot use it to store your disk key, for example, but you can use it to collect your boot time measurements and use it to basically remote attest yourself to a relying party. So, so this is good progress, but yeah, it's still a big chunk of C code running in SVSM kernel mode, which is something I really hate. But it's like it is, and we are making work on moving that over to user mode, which brings us to the progress we made on user mode support. So actually, most of the pieces are now in place. So we have virtual memory management, RAM file system, and so on. We can switch tasks. We have even user space entry exit code. Elf loader was actually the first thing we had. And yeah, a very simple system code dispatcher. That's one of the things we need to get ready for full user space support. I'm currently working on a user mode support library because that's something we need, like a heap allocator in Rust and a basic library. Long-term or mid-term goal is actually to enable COCONUT user space as a Rust target so that we can use standard Rust. Basically, it's a Rust standard library to develop COCONUT modules. So there are still some way to get this usable, but I think we are on track for that. So this was a rough overview over the progress that we made in the last year. Now let's get to the plans for the next year and beyond that. I already mentioned the user mode support library with the heap allocator and the system core interface. We have a basic design. Work has started on implementing that. All of this should lead to, or will lead to, a basic user space infrastructure that we are building up with some kind of inner process that's pure responsibility is to actually launch the other services like VTPM and other services you want to run in the SVSM context, or that the SVSM should provide to the guest OS. Another example is the UEFI variable store that people keep talking about. So so this is the plan for the user space part. Another very important thing that we want to support in the SVSM is having the SVSM support an APIC, or making the SVSM own an APIC, which is currently a bit problematic, but it's an important thing to have before we can actually move on with native platform support and with TDX platform support, because on these platforms we need to have IPI support in the SVSM to do things like remove TLB flushes. So this is something we need to work on, to basically have an IRQ infrastructure and support for an interrupt controller. We'll get there more deeply in the challenges part of the talk. One thing that is probably going to surprise you, but we plan to use the TPR, which Linux does not use, but we plan to use it for certain things on prioritizing IRQs. Another thing which mostly touches the SVSM or the COCONUT kernel is to finish the virtual address space split. So currently the SVSM uses a direct map like the Linux kernel does, which is kind of against the goals of the isolation goals of the COCONUT SVSM. So we want to finish up the address space split, basically having the address space split up into a global shared part, into a per CPU part, into a per task kernel part, and into a user space part. Each of these parts will get its own heap, and so we can keep everything nicely isolated. We want to move to a page table self map, which is kind of a requirement when you get rid of the direct map. So that's work that has not started yet, but that's on the list of plans. And of course, we want to develop the SVSM, or we want to get the SVSM to a point where it can be a paravisor for all kinds of operating systems, for unenlightened operating systems, and finally also run, of course, Windows in a confidential VM, where this is where paravisor support is basically the requirement for that. For those of you that were at Plumbers, you have probably seen the announcement around OpenHCL, which contains all the paravisor user space support on top of a Linux kernel. Something I really would like to dive into is getting this run in user mode on COCONUT. So when they open sources, we will see how difficult it is to make COCONUT ready for that. So this was the very rough overview of the plans we have for COCONUT in the time to come. Now let's dive into the challenges part. What challenges do we face? The challenges are mostly towards hypervisor support and features we do not yet have in the hypervisors we developed the SVSM for. And since we are here at KVM Forum, I will focus on the KVM part. So the first thing is actually a very small thing, but I don't know how difficult it is to implement. Something I would really like to see, and something we need to run Windows on in a confidential or in an SEV-SNP guest is support for VTOM, the virtual top of memory, which basically is a feature of SEV-SNP where you can configure a guest physical address, and everything, and the hardware will treat everything below that physical address encrypted and everything above that guest physical address decrypted. that basically turns the C bit we currently have in the SNP page tables into a shared bit, because we can set a specific bit and make an address shared, basically, or have the shared version of that address. What we need for that is basically a way to mirror the PGD entries in the top level page table to above the boundary. So basically, we can set vterm to a 512 gigabyte boundary with 4-level paging and have basically an unencrypted mirror of guest physical memory above the vterm address. Right. That should actually come before that. So now to the next challenges, and that will be covered by Roy because he is mostly working on that.
Yeah, so continuing on with the challenges, I'm going to start with the synchronization of register state from user space to KVM and through to the VMSA. When you're working with SEV-ES and SEV-SNP, the register state is preserved during the guest exits and entries in the VMSA. So the VMSA is encrypted because, of course, that register state may contain sensitive information. But there's actually one instance where that VMSA is not encrypted, and that's when the guest is being launched. And that's because the hypervisor is responsible for populating the initial state of the CPU into the VMSA, which is then applied to that CPU as it started. So if we look at the startup for a SEV-SNP guest, you'll see that all of the pages that are pre-populated into the guest GPA range go through this process of being measured. And so that's via this launch update mechanism in the security processor, which will look at the plain text contents of the page. It will look at the GPA that page is located in, and then it will measure that into a launch digest, and then it will encrypt that page. And when that process is complete, you get to the launch finish, where the launch digest is finalized. Now, the VMSA pages, so this initial configuration of the CPUs, forms part of that measurement, and the location of that GPA, the location of the VMSA in the guest physical address spaces also forms part of that measurement. Which means that if any changes are made to the VMSA, if it's not what's expected, or if it's at a different location, you get a different launch measurement. And then when you do your remote attestation of the report that includes the launch digest, you won't get a match, and you won't be able to verify your guest payload. So the problem that we have is that the initial state of the CPU is set via the IOCTL's KVM set regs, set sregs as well. And then, so KVM builds up a picture of what the CPU is configured to launch as. And then when you get to the KVM SEV-SNP launch finish IOCTL, so when you finish configuring the guest, KVM will take that register state. It will then build its own picture of the VMSA. It will then put that at a specific location in the GPA range, and then it will update that and measure it. But the problem is that not every VMSA entry, not every VMSA field can be set via that mechanism. And also, we've seen, as we've been developing this, there's been changes in the kernel. The floating point registers weren't synchronized at first. SEV features forms part of the VMSA as well. And that has changed based on kernel configuration and kernel versions as well. And it became a problem for us because we've actually got a test. There's a PR waiting to merge in COCONUT-SVSM that actually will verify the launch measurements. And we can't really get that merged at the moment because the launch measurement doesn't work on every platform. So what we're looking at is a way to directly set the VMSA bypassing the standard way of doing it in KVM. And actually, it's pretty straightforward using the existing IOCTLs. So what I've done, I've put a POC together, which modifies the. Is that on the next one? Yeah. So it modifies the launch update IOCTL to allow it to set a VMSA page. That's nothing controversial, so because the security process is just another page type in there. But it's at the moment, launch update doesn't support VMSA pages. There's a couple of things that we have to do when you do that. The first is that obviously when you're providing a VMSA like that, you have to associate it with a vCPU. So that information has to be passed into that IOCTA, which it wasn't before. And at the moment, there's an unused flags field, certainly in the version of the kernel I'm looking at. I think it's moved on a little bit since. But I'm using that unused flags field to set that vCPU ID and associate those together. And then when we've actually updated the initial state via this mechanism, we keep track of that via a flag. And you can see it on the right there, there's a VMSA updated equals true. And the reason for that is when we get to the launch finish stage, what normally happens with KVM, as I said, is it will synchronize the state from its register state into a VMSA and it will measure that. We don't want to do it in this case. So it just checks that flag. Has user space already provided a VMSA? Yes, okay, we'll bypass that. So that allows us to actually have full control over the VMSA and also the location of it as well in GPA. Now, this is important when you're using, like, Jörg mentioned, we're using IGVM now. IGVM gives you free flexibility to put whatever you want in that VMSA and locate it wherever you want. So that solves the problem for us. There's a couple of things left to complete. The first is I think I might have to go and revisit, see if we need to add support for SEV-ES in this. But there's another one, which is that, okay, so we're now setting VMSA state via user space. We ought to synchronize that state back to KVM's initial state, so at least it knows the startup state for the CPU. Once it gets running, all bets are off because, of course, the VMSA is encrypted, but we ought to sync that initial state back again. Okay. So the next one, here we go again, VMPLs and KVM. A lot of talk has happened over the last few days about this. Tom had a great presentation this morning about this, so I'm going to skim over a lot of this, and I haven't got much time anyway. But in COCONUT, we need VMPL support, and it's holding us back a little bit that it's not there. So I actually started looking at this from a COCONUT-SVSM perspective to get something up and running for us, but also to be able to help us to contribute to any upstream work that's going on. So I won't go into what VMPLs are and how they work. I will give a quick example of why we need it in COCONUT-SVSM. Tom mentioned this morning it's useful for VTPMs. If you have a VTPM implementation running under COCONUT-SVSM kernel in the guest, it means it's isolated from the host. Fantastic. But without memory isolation from the operating system and the operating system firmware running below that, that could the kernel could go along and scrape the TPM memory. It could reset the PCRs. It could do all sorts of things that basically invalidate the usage of a VTPM. So we need VMPL access to be able to prevent that from happening, to isolate the operating system from the SVSM kernel. So obviously we haven't got upstream support for VMPLs at the moment. Loads of work's already been done on this. Loads of discussions have been going on. We've already talked a lot about this, and the Q&A after Tom's talk sort of showed that. There's a few requirements that we have from a COCONUT-SVSM perspective. We need something that is going to support multiple architectures, and we don't want this re-implemented every single time. SEV-SNP, TDX, VSM, possibly more than that. But we also need something high performance. So the current sort of work to do the VMPL switches in user mode needs certainly optimization added to it to do that switching inside KVM. And it's worth mentioning again that TDX and others can enter the guest in one privilege level and come out in another. So we need to be able to support that. And at the moment, the one thing we really need to be able to support for COCONUT-SVSM is an APIC per VMPL to be able to deliver interrupts to any of the VMPLs. So with that, I wanted to get something working that we could run COCONUT-SVSM on. And so I picked the easiest starting point, which was Tom's patch series, the RFC patch series, because he's already done all of the hard work to manage the switching of VMPLs. And also, storing the state of the different VMPLs when you're doing the switching. What I wanted to do is add at least support for APIC on top of that. I tried two approaches. The one on the left is Tom's first option, if you saw his talk this morning, which was to just create effectively a save area within the CPU to save the state from each VMPL and restore it when you switch. And I won't go into much more detail on that. The one on the right is a little bit more interesting because this is a sort of hybrid approach where you create a KVM vCPU for every VMPL. So you have multiple KVM vCPUs per virtual CPU, and they're stored in an array, but it's not exposed to user space. So as far as user space is concerned, you still have the one vCPU. KVM is the one that manages the multiple CPUs internally, and this is part of that optimization path. And the way it's done, I'll switch this one to see how it's done, it's easier to see, is what I've done is an extract. You might not be able to see it, so I'll just describe it. I've created a new structure which manages the overarching state of a vCPU from a VMPL perspective. So it's got an array of 4 KVM vCPUs in there, 1 for each VMPL, and it maintains the current VMPL. And what we do is we add a pointer to that structure, the same pointer to all of the struct KVM vCPUs for a particular vCPU. And I'm using the word vCPU so many times, so this does get a little bit confusing. But basically, we have an array of 4 KVM vCPUs, 1 for each VMPL. And because that's stored as a member inside there, it means that you can easily switch between them. You can have a pointer to the VMPL2 struct KVM vCPU, look at the array inside that, and then actually work out what the relevant structure is for VMPL0 as well. Now, this is a sort of reverse problem to saving the VMPL state, because you have to save the common state. From any of those vCPU pointers, you need to work out what the APIC ID is. You need to be able to hold the mutex on the vCPU itself. So what I've done is I've refactored the common code, and this isn't an exhaustive list, it's just an example, into a substructure inside the vCPU. Now, this is probably the least palatable part about this solution, because what that means is that everywhere that you access that common state over the KVM code, you have to modify it to use the substructure. So yeah, if you look at, I've put an RFC patch series on the list just to show you what it looks like. First patch in that series touches many, many files in many, many locations, although they are trivial changes. But with this, it means that a switch of VMPL level is as simple as just updating the pointer to the vCPU structure that you are using. So when you call the run function, you select the VMPL structure and pass it to the run function. If it changes whilst you're in the run, when you come out the run loop, you say, okay, the VMPL has changed inside the guest, and you can switch which pointer you refer to. So there's some other bits and pieces that you need to do to support this, but actually it's fairly minimal. The creation and destruction logic obviously needs updating. I mentioned APICs. This allows you to have independent APICs per VMPL. We have to choose which one to target when you're delivering interrupts. We're testing this with COCONUT-SVSM. We're only supporting interrupt delivery into VMPL2 at the moment, so it's hard-coded to go to VMPL2 as per Tom's patches as well. And I've already mentioned about the fact that the guest can switch VMPL, and we handle that on exit. I struggled with this slide. I updated this over the last few days because the what next looked very different until some of the discussions happened over the last week, so I've just left it in an unfinished state. But basically what next is we need to carry on these discussions about it. I think everyone's a bit more aware about the sort of requirements that are coming up, and we're sort of getting to the point where we could converge on a solution. I believe there's a BOF happening later today. I don't know when or where at the moment, but that's hopefully some more on this what's next slide is going to be coming out of this. So that, I think, is a good place to stop, and we've got a few minutes for questions, I believe. So, oh, there's lots.
Hey there. So you guys probably talked to some of the ARM folks, maybe even the RISC-V folks, I guess, in Plumbers last few days. So how confident are you in this new hybrid solution that's gonna be compatible with whatever they come with for realms and RISC-V, whatever? I don't recall what the terminology they use for RISC-V. I don't know.
So the ARM side is coming up with ARM planes, which kind of looks like TDX partitioning in a way. So for that, I'm pretty confident that it can be easily supported once we can support TDX partitioning. within the code base for RISC-V. I don't know whether they are planning something like that at all. Yeah, they are planning a confidential computing extension, but I don't know about any plans to support like the privilege level concept. So.
But if we have 3 architectures that are able to do this, this might force them to actually consider that, right? They're still in design phase, so.
Right. Well, one of the main reasons this privilege thing exists is to run Windows, right? And RISC-V does not run on Windows. Windows does not run on RISC-V that way, but they might come up with something like this, and if they do, since CoV also looks pretty much like ARM realms and TDX, it's probably going to be identical. So,
thank you.
Correct me if I'm way off, but this is all about running unmodified guests on Coco VMs, right? If that's the point, I'm trying to understand, does it even make sense to run unmodified guests? Surely the guest needs to be able to interact with the Coco hardware and reason about the attestation report, and you need all sorts of modifications for it to actually really be useful.
So the full paravisor support is targeting mostly unmodified guests. Even Windows is not completely unmodified. But there's also the use case of an enlightened OS that just needs services in a secure way, like a VTPM. You cannot emulate a VTPM on the host, right, for a confidential VM. And that is also an important use case for privilege levels in these architectures.
How do you IPI specific VMPLs? How do you select? Do you have a special hypercall and it's through the hypervisor, or?
Yeah, can do. Which in particular was that, sorry?
My question is, how do you select which VMPL you're targeting with an API from a privileged context?
Well, APIs target the same VMPL, do they not? From
surely there's no way of targeting a lower privilege API.
You can do it would be possible using this, but I haven't done anything with those at the moment. This is a very quick implementation just to start it off.
So for the load VMSA functionality, one problem that you have is that basically in some cases KVM needs to know exactly what goes in the VMSA, because especially the SEV features, they affect what you are doing. So you also need to validate that you are not putting anything that KVM doesn't know about. And then there are problems because, for example, you may want to put something in there because anyway KVM cannot control your XCR0 and XSS contents. Those are part of the encrypted state. So you may want to put something in there to kind of bootstrap the functionality, but at the same time, you cannot put anything in there because KVM doesn't know what is at that offset. So this is why currently the design is that you cross fingers that the state matches. I think we mostly should have gotten it right with the new API that has VM types for SEV-ES. If we didn't, that's a problem. I would prefer not to have that, but certainly we can have, for example, the custom GFN if that helps. We need to look at what's missing case by case, essentially.
Okay, yeah, you're right about the validation. So at the moment, we've so the QEMU IGVM implementation, which is under review, does IGVM. Sorry, it does VMSA validation, and then the validation is it something we can support to send up to KVM? You know, are there any fields that we cannot synchronize? And I envisage actually moving that, if we go with this solution, moving that into KVM, so it says, is this something we can support? If not, it will fail that update. So we can actually validate that. But yeah,
can we swap that logic? Can we swap the logic and just have a call that says, give me the VMSA? At which point user space can compare?
No, because the VMSA has been pre-prepared by the guest owner and measured as part of the IGVM file, or if you're using IGVM.
Yeah, user space can be the one that fails. So instead of having kernel space do the validation, you can have user space do the validation, and then yes, if it doesn't match, it fails.
No, absolutely, yes, you could do that.
That makes the interface way easier because you don't need to go and put all that validation logic into
Right.
KVM, you just say, give me the current picture that you have of the world that is a VSMA format instead of my other getrecs, and you
that's a great idea.
are out of time.
Yeah, we're out of time. No, that is a great idea. Yeah, thank you. All right, thank you, everyone.